Swayam Prabha. Digital India. Educated India.
In the previous two lectures, we have discussed the properties of Fourier transform, Fourier sine transform and Fourier cosine transform, and also we have discussed the application of these properties, that if I know the Fourier transform of a function, using the properties of Fourier transform, I can find out the Fourier transform of other complicated properties. So, let us discuss some more properties and the applications of those properties which we have not done. The first one is Fourier transform of x to the power n f x. This is equals minus I to the power n dn d alpha n of f of alpha. Similarly, Fourier sine transform of x f x. This is equals minus d d alpha of Fourier cosine transform of alpha. You see here, in case of Fourier sine transform, it is becoming minus d d alpha of Fourier cosine transform of alpha, and Fourier cosine transform of x f x. This is equals d d alpha of Fourier sine transform of alpha. Let us see the proof of the first one over here. Number 1, your f of alpha, we know it from the definition 1 by root 2 pi minus infinity to infinity f x into e power I alpha x into dx. Therefore, from here, if I have to do d d n of f alpha, d d n d alpha n of f alpha, this equals, you can write down 1 by root 2 pi minus infinity to infinity. This will be equals to f x into not e power. So, each time you are making the derivative. So, at the nth time I am writing it directly, it will be I x whole to the power n into e power I alpha x into dx. Or in other sense, this term I have written directly, otherwise I have to show what is d dx of d d alpha of f alpha. From there, I have to show d square d alpha square. Since this type of thing we have done for the case of Laplace transform. So, directly I am writing, because internally you are making the derivative inside, differentiation under the sign of integration cases. So, this I am writing f x after nth derivative will be I x whole to the power n into e power I alpha x into dx. So, I power n will go outside. So, it will be I power n into root over 2 by pi minus infinity to infinity f x into e power f x into, this will be x to the power n will be there into e power I alpha x into dx. And this is equals to I power n into, what is this? 1 by root 2 pi minus infinity to infinity f x into x to the power n into I alpha x. So, what is your function? If I assume this, that this is my function, say new function, say g x, which is equals f x into x to the power n, then I can tell 1 by root 2 pi minus infinity to infinity, this g x into e power I alpha x dx is nothing but the Fourier transform of g x. So, this I can write down Fourier transform of f x into x to the power n. So, I think it is clear. Fourier transform of f x into x to the power n, this is equals to 1 by root 2 pi minus infinity to infinity f x into x to the power n into e power I alpha x into d alpha. Therefore, Fourier transform of f x x to the into x to the power n, this is equals 1 by I to the power n into dn, from here dn d alpha n of f of alpha, and this I can write down I to the power n. So, this is minus I can make it. So, minus I to the power n dn into d alpha n of f of alpha. So, Basically, I am getting the proof of this one, that Fourier transform of fx into x to the power n. This 1 by I to the power n, always I can write down minus 1 whole to the power n into dn d alpha n of f of alpha. So, let us see quickly these three things we have to prove. We are proving the first one. I am starting with f alpha equals this, and dn d alpha n of f alpha, if I make the derivative of this function n times, then in the integral I will obtain ix to the power n into e power I alpha x. This we can show it by making first d alpha of f alpha is what, then d square d alpha square. So, that thing I have skipped, because we have shown it in the case of Laplace transform. So, I power n I am bringing outside, and once I power n I am bringing outside 1 by root 2 pi minus infinity to infinity. This one is nothing but Fourier transform of fx into x to the power n. So, once I am getting this one, Fourier transform of x to the power n f alpha, then I can write down Fourier transform of x to the power n fx equals 1 by I to the power n dn d alpha n of f alpha, and this I can write it as minus I to the power n dn d alpha n of f alpha. This completes the proof of the first one. Let us see the proof of the second one now. Fourier, I am starting with Fourier cosine transform of alpha. This we know that root over 2 by pi 0 to infinity fx into cos of alpha x into dx. This we know from the definition that Fourier cosine transform of alpha is root over 2 by pi 0 to infinity fx cos alpha x dx. And once I have written this, therefore, what is your dd alpha of Fourier cosine transform of alpha? dd alpha of Fourier cosine transform of alpha, this is nothing but root over 2 pi pi 0 to infinity. Your dd alpha is there, that is fx into dd alpha of cos of alpha x. I can write down. I can bring this under integration inside the integral sign, so that if I integrate this, if I differentiate this, cos of alpha x is there. So, minus will come x fx into sine of alpha x dx. And what is this? This part is nothing but, this integral is nothing but the Fourier sine transform of x fx, root over 2 by pi 0 to infinity x fx into sine of alpha x dx is the Fourier sine transform of Fourier x fx. So, that we can write it as minus Fourier sine transform of x into fx. Therefore, I can write down Fourier sine transform of x fx. This is equals to minus, this is equals minus dd alpha of Fourier cosine transform of alpha. So, this completes the proof that Fourier sine transform of x fx equals minus dd alpha of Fourier cosine transform of alpha. In the same fashion, I can prove that Fourier cosine transform of x fx, this will be equals to, minus will not be here, dd alpha of Fourier sine transform of alpha. This we can write down. So, therefore, this we have proved, and on the same fashion we can prove this part also, which you can check it of your own. So, let us again go back to this. This already we have shown. For the proof of the second part, we starting with Fourier cosine transform of alpha equals this integral from definition. From here we are writing dd alpha of Fourier cosine transform of alpha as this, and this is equals minus root over 2 by pi 0 to infinity x fx sin alpha x, which is nothing but again Fourier sine transform of x fx. So, I am just writing minus Fourier sine transform of x fx. So, we can tell Fourier sine transform of x fx equals minus dd alpha of Fourier cosine transform of alpha. And similarly, as I told, the third proof you should do it of your own. Now, let us see the next theorems. Number 1, Fourier transform of f dash x, that is derivative of a function. If I know Fourier transform of a function, then the derivative of the function, Fourier transform of the derivative of the function can be expressed in terms of Fourier transform of that function. Again, this is similar properties we have studied whenever we were doing the Laplace transform. So, the first one is Fourier transform of f dash x is equals to minus I alpha into Fourier transform of x if f x approaches 0 as x approaches plus minus infinity. Now, this particular condition is required. Whenever we will prove it, we will tell why it is required. This condition that as x approaches plus minus infinity, f x approaches 0. Similarly, number 2, Fourier sine transform of f dash x equals minus alpha into Fourier cosine transform of alpha, where f x approaches 0 as x approaches infinity. This is obvious because for Fourier transform the interval is minus infinity to infinity, whereas for Fourier sine and Fourier cosine transform x approaches 0 to infinity. Similarly, for Fourier cosine transform of f dash x, this will be equals to alpha Fourier sine transform of alpha minus root over 2 by pi f of 0 when f x approaches 0 as x approaches infinity. And the double derivative also we have shown, Fourier cosine transform of f double dash x equals that quantity, Fourier sine transform of f double dash x is equals to the quantity of this one minus alpha square into Fourier sine transform of alpha plus alpha root over 2 by pi into f of 0. Here only one thing is there. In the first three cases only f x approaches 0. So, whenever I am taking the second derivative, then not only f x, but f x and its first derivative, but that is f dash x both should approach 0 whenever x approaches infinity. So, let us see the theorems, proofs of the theorems one after another. So, the first we have to prove that Fourier transform of f dash x equals minus I alpha into f of alpha whenever f x approaches 0 as x approaches plus infinity or minus infinity. I am starting with the left hand side, that is Fourier transform of f dash x equals 1 by root 2 pi minus infinity to infinity e power I alpha x into f dash x dx. This is equals 1 by root 2 pi minus infinity to infinity e power I alpha x into f dash x. You can write down d of f x form, d of f x into dx. So, that now I can take it one as the first function, other one as the second function, and I can use integration by part and I can integrate it by integration by parts. So, by integrating using integration by parts, the first one will be e power I alpha x into d of f x was there. So, it will be simply f x, where x will vary from minus infinity to plus infinity, minus, if I integrate this I alpha will come out, I alpha minus infinity to infinity into f x into e power I alpha x into d x. And what I know? I know that f x approaches 0 as x approaches plus infinity or minus infinity. This I know it. So, that this value will vanish. Now, you can understand that I need the value of f x at this point, and if f x is 0 at x equals plus infinity or minus infinity, then the first term will vanish and the second term will be I alpha into, this is nothing but 1 by root 2 pi minus infinity to infinity f x e power I alpha x dx is nothing but Fourier transform of x f x, and which I am writing f of alpha. So, f of alpha is nothing but Fourier transform of f x, which is the quantity 1 by root 2 pi minus infinity to infinity f x into e power I alpha x into dx. And please note one thing here. So, this completes the proof that Fourier transform of f dash x, this is equals to minus f of alpha minus I alpha into f of alpha. I am not giving the proof, but please note down this thing. Fourier transform of f n x, nth derivative of the function. If I know the Fourier transform of f x, then Fourier transform of nth derivative, I can show it simply minus I alpha whole to the power n into f of alpha. Obviously, if f dash, f double dash, like this way, if n minus 1 approaches 0 as x approaches plus minus infinity. In the same way, by induction I can prove this one. You can try it of your own, that Fourier transform of f n x equals minus I alpha whole to the power n into f of alpha, where the condition is, please note this one, that f dash, f double dash up to f n minus 1 x approaches 0 whenever x approaches plus infinity or minus infinity. So, again let us see it quickly. These things we had to prove, and for the first proof I am starting with Fourier transform of f dash x. In the integrand, f dash x I am writing as d of f x, so that I can use one as the first function and other one as the second function, and I will use integration by parts. Using integration by parts, I am getting these two things. The first integral, the limiting value of the first integrand will be 0, because f x approaches 0 whenever x approaches plus infinity or minus infinity. It is known to us. So, that is 0, and second integral is nothing but the minus I alpha into Fourier transform of f alpha f x. So, Fourier transform of f x, which we are writing as capital F alpha, from the definition we can write down. Therefore, this completes the proof that Fourier transform of f dash x equals minus I alpha into f of alpha. And on the same way, we can prove that Fourier transform of f n x, this is equals minus I alpha whole to the power n into f of alpha, whenever f dash, f double dash, f n minus 1 x approaches 0 as x approaches plus or minus infinity. Now, let us see the second one. Second one, Fourier sine transform of f dash x. On the same way, we can approach root over 2 by pi into 0 to infinity f dash x into sine of alpha x dx, and I can write it as root over 2 by pi 0 to infinity f dash x, I will keep it as it is, sorry, sine of alpha x I am writing, and f dash x is d of f x into dx. Use the integration by parts now, root over 2 by pi into f x sine alpha x 0 to infinity minus alpha into 0 to infinity f x cos of alpha x into dx. So, the first part will vanish, this part will be equals to 0, because f x approaches 0 as x approaches infinity, and at 0 automatically it will be 0. So, this first value is 0, so that I can write down minus alpha into root over 2 by pi 0 to infinity f x into cos of alpha x dx, and this integral is known to us. It is nothing but Fourier cosine transform of the function f x, which we are writing as f c of alpha. So, this completes the proof that Fourier sine transform of f dash x, this is equals minus alpha into Fourier cosine transform of alpha. On the same way, the third one also you can prove it. This proof is Fourier sine transform of f dash x equals minus alpha into Fourier cosine transform of alpha. In the same way, you can prove Fourier cosine transform of f dash x. This is equals my alpha into Fourier sine transform of alpha minus root over 2 by pi f of 0. Because I don't know the value of f0. So, in the same fashion, whatever way I have shown, you can prove it of your own and you should do it of your own. Of course, here again your f(x) approaches 0 as x approaches infinity, and for that reason here also this value was 0. So, again let us say quickly the second one, that is Fourier sine transform of f dash x I am finding out. So, this is root over 2 by pi sin alpha x into d of f x. This I can break it into using integration by parts. The limiting value of the first term will be 0 because f x approaches 0 as x approaches infinity, and second integral is nothing but Fourier cosine transform of the function f x. And so, this integral first term vanishes and second integral is nothing but this one. So, minus alpha into Fourier cosine transform of alpha, which completes the proof that Fourier sine transform of f dash x equals this quantity. On the same way, the third one we can prove it, you can prove it of your own, which is Fourier cosine transform of f dash x. You can find out like that way. Let us see the proof of the fourth one, that is Fourier cosine transform of f double dash x. This is equals root over 2 by pi 0 to infinity f double dash x into cos of alpha x dx. From the definition we can tell this one. So, this equals root over 2 by pi 0 to infinity cos of alpha x into d of f dash x into dx. Now, use again integration by parts over here. So, you can write down root over 2 by pi f dash x into cos of alpha x, x varies from 0 to infinity, plus alpha into 0 to infinity f dash x into cos was there. So, it will be sine of alpha x into dx. So, therefore, this equals again the first part will vanish because we know this thing, not vanish, fully vanish. At infinity this will vanish because f x and f dash x approaches 0 as x approaches infinity, but at x equals 0 you will get a term. So, this is sin cos 0 is 1. So, you will get f dash 0. So, basically minus root over 2 by pi, at 0 it is negative. So, minus root over 2 by pi f dash 0 plus alpha into, this is nothing but again root over 2 by pi into 0 to infinity f dash x sin alpha x dx is nothing but Fourier sine transform of f dash x. So, that I can write down this is nothing but Fourier sine transform of f dash x. So, therefore, this equals minus root over 2 by pi f dash 0 plus alpha into Fourier sine transform of f dash x. Using the earlier property, I can write down minus alpha into Fourier cosine transform of alpha. This the property we have proved just now. So, this is equals minus root over 2 by pi f dash 0 plus alpha into minus this value is equals to this thing. So, this if I write down minus, this will be equals to minus alpha square into Fourier cosine transform of alpha minus root over 2 by pi f dash 0. So, this way I can tell that Fourier cosine transform of f double dash x equals minus alpha square into Fourier cosine transform of alpha minus root over 2 by pi f dash 0. And similarly, you can prove the fifth one also, that is Fourier sine transform of f double dash x. This is equals to minus alpha square into Fourier sine transform of alpha plus alpha into root over 2 by pi into f 0. Here again f x and f dash x both approaches 0 as x approaches infinity. So, please note this thing, that number 5 we can prove it, you can prove it of your own on the same fashion as we have proved the fourth one. So, let us see the fourth one, Fourier cosine of f double dash x I am finding out, which is root over 2 by pi 0 to infinity f double dash x into cos of alpha x dx, and this I am writing d of f dash x. Now, I am integrating by parts, we have already shown. So, we are getting minus root over 2 by pi alpha Fourier sine transform of f dash x, and using the earlier property, Fourier sine transform of f dash x is nothing but minus alpha into Fourier cosine transform of alpha. So, that this equals, I can write down Fourier cosine transform of f double dash x is equals to minus alpha square into Fourier cosine transform of alpha minus root over 2 by pi into f dash 0. This completes the proof of the fourth one. And on the same fashion, we can prove the fifth one also, as I have mentioned earlier, which you should do it of your own. The next theorem, the earlier theorem was on the differentiation of the Fourier series of a function. If I know the Fourier transform of a function, then what should be the Fourier transform of the differentiation of the functions that we were studying. Now, we will start that if I know the Fourier transform of a function, if I integrate the function, then what should be the Fourier transform of that function. Here we are saying Fourier transform of a2x fx dx is equals to f of alpha by minus I alpha. So, let us see the proof of this one. Fourier transform of a2x fx dx equals f of alpha by minus I alpha. I am assuming this thing, let phi x equals a2x fx dx. Phi x equals a2x fx dx. So, that this implies phi dash x is nothing but, it will be, if you use differentiation under this, you will obtain phi dash x, this is equals to f x. So, that Fourier transform of phi dash x using the earlier properties, I can write down minus I alpha into Fourier transform of phi x. This is equals again minus I alpha into Fourier transform of phi x is nothing but a2x phi x dx. This a2x, not phi x, but this is fx dx. Phi x is a2x fx dx. Therefore, from here I can write down Fourier transform of a2x fx dx. This is nothing but minus I alpha will go on that side. So, 1 by minus I alpha into Fourier transform of phi dash x, and Fourier transform of phi dash x is nothing but minus I alpha into Fourier transform of this phi dash x is f x. So, 1 by minus I alpha into Fourier transform of f x, and this equals, I can write down Fourier transform of f x is nothing but f alpha by minus I alpha, which completes the proof that Fourier transform of a2x fx dx, this is equals to the Fourier transform of f x divided by minus I alpha. Let us see it quickly. So, I have to prove this. that Fourier transform of a to x f x dx equals f alpha by minus I alpha. So, I am assuming phi x is this, so that your phi dash x is f x, and now I am taking Fourier transform of phi dash x equals using the property minus I alpha into Fourier transform of phi x, which is equals to minus I alpha into Fourier transform of phi x is a to x f x dx. And so, I can tell Fourier transform of a to x f x dx minus I alpha by Fourier transform of phi dash x. Again, phi dash x is f x, so I am replacing it, and I got the result that Fourier transform of a to x f x dx equals Fourier transform of f x, that is capital F of alpha minus I alpha. So, if I know the Fourier transform of a function, and if I integrate that function from some range a to x f x dx, then what will be the Fourier transform of that integration of the function, that I can find out from this particular theorem.